one question. Oh, thank you. With one question after each talk, and we are then going to have a few minutes towards the end of the whole session to discuss and open up, and we'll open up the floor to everyone present here. So let's start with our first speaker, Devin Silvia from Michigan State University. Devin is a director of the undergraduate studies and specializes in teaching computational math, science, and engineering at MSU. Devin is also passionate about providing quality STEM education and inclusive learning environment. And I would request Devin to start the talk, and the floor is all yours.
Perfect. Thank you for the introduction, and I'm excited to be here. I appreciate Mike extending the invitation to be part of this seminar today. And so let me get my slides pulled up here and we'll dive in. Okay, great. So hopefully everyone can see that. Can you hear me okay? So I'm going to jump in here. The talk that I give today might be a little bit different than what some of my co-presenters are giving. Of course, I don't exactly know what they'll say because I'm going first. But what I'm going to talk about today is how we've been teaching sort of interdisciplinary computing at Michigan State University, specifically trying to develop students' ability to do computational modeling and data analysis. And at the end of my little 8 minutes, I'll try to talk about how this has been used to facilitate the integration of computing across astrophysics and physics at MSU. And highlighting how they've been integrating into the curriculum. And so rather than teaching pure computational astrophysics, I'll kind of talk about this interdisciplinary approach that we've been doing. And my background is actually in computational astrophysics. And so I think that's probably why I've ended up here today, and my role has evolved over the years. But what I'd like to do first is, in the introduction, as was said, I'm a member of the faculty in Computational Mathematics, Science, and Engineering department at Michigan State, which is a lot of words thrown together that seem familiar individually, but perhaps are unclear when you start stitching them all together. And so I like to highlight when I start these talks is what is CMSC. And so we're housed both in the College of Engineering and the College of Natural Science at MSU. We're sort of intentionally interdisciplinary. And when you think about why does a department like CMSC exist, why do we have folks from physics, chemistry, material science, electrical engineering, all sort of stuck together under one roof? The reason for that is MSU sort of saw that as the world was evolving and becoming more computing driven and more data driven, they wanted to create a space on campus for scientists whose scientific discovery and research was driven by the development and use of computational tools. And so let's put those people together who often have joint appointments across many other departments on campus, and try to create a space where they can collaborate, learn from each other, benefit from each other, and sort of advance their computational research agendas. And so unlike a traditional computer science department, which we actually have one of those at MSU, where computer science is often focusing on the science of computing, we're really focusing on using computing to do science. And so we have folks from astrophysics and physics who exist in our department, who help teach some of our courses. And so they bring that perspective and flavor into the room. But we also have horticulturists who are also thinking about how they can be using these tools to integrate computing into the classroom. And so when we talk about this from an education perspective, one of the things that we as a department were tasked to do was try to teach computing in an applied way outside of a traditional computer science classroom, and really start designing what might be considered a computational science or data science type course. We chose to do Python because that's sort of the common introductory coursework. And so we're getting a population of students often that end up in our classrooms who don't have any prior programming experience, but have self-identified in some cases or are required to be there. The need to develop computational skills to apply to their discipline. And in the early days, many of these students were physics and astrophysics students. And so the course that we came up with is what we call CMSC 201. It was originally labeled Introduction to Computational Modeling and Data Analysis. It's since evolved because we now have a 2-semester sequence. So it's Computational Modeling and Data Analysis 1, and there's a 2 that follows it. And really, it is intended to be this sort of intentionally interdisciplinary approach to learning to do computational work. Okay. So if we just look at some of the learning goals for this course, I'll go through rather quickly. We really want students to use computational algorithm and tools to gain insight into physical, biological, social systems. Whatever their disciplinary expertise is, how can they use algorithms, computation to actually better understand those systems that they're interacting with? How do they actually write code? So we have to teach them to program, of course, to solve those problems within whatever discipline they are. This requires identifying how you deconstruct a system and turn it into a algorithm or a computational model. We want them to be able to work with data, analyze data, visualize data, whether that's data is coming from observation or experimentation or coming from simulation like computational astrophysics, and be able to work and interact with that, apply some basic numerical methods to solve those problems, and ultimately synthesize those results into something they can present both verbally and writing. So we create opportunities for students to do that. How do we try to approach this with the learner in mind? We've tried to develop a learner-centric class. And so our design choices have all been centering the student, trying to give them opportunities to grapple with these skills and develop them. And the approach that we've taken is what we sort of think about as an integrated progression, where we thread together three sort of main areas: some sort of modeling or data analysis concept, choose some sort of context or application that's relevant to at least some fraction of our students in the classroom. Because we have a very diverse student pool, we can't necessarily hit everyone all the time. And then, of course, we have to teach the programming practices and tools as well. And so I'm going to fill out this table here and then highlight just one section of it. So this is a series of assignments as we sort of go through and thread together these three main areas. So one example of an assignment might be thinking about how we can get students to go from mathematical representations of physical systems into actually writing the code to do it. And we might do the context of kinematics or projectile motion to sort of relate to and connect with those physics and astrophysics students that might be in the room. And the programming skills, if this is early on in the course, might be as simple as defining lists to store information about some sort of time evolving system. And of course, writing loops to do the time evolution. Okay. And so we're threading these things together. So it's never a programming concept taught sort of by itself with some sort of contrived examples, but really it's always applied to a specific problem where the students are sort of having to grapple with, how do I break this problem down into code? And then also, how do I write the code that's going to solve the problem? And so it's intentionally integrated together. How we implement this, what does it look like? The approach that we've been using, we use Jupyter Notebooks, which I'm sure many people on this call are very familiar with. It used to be I sort of had to advertise to folks, hey, if you haven't played with Jupyter Notebooks, check them out. But they're really nice for a variety of reasons, which I'll talk about in a second. But we also try to create an active and collaborative learning environment by taking a flipped classroom approach to the way we teach our students. And so prior to coming to class, they do some pre-class assignments, they look at some materials, they work through some exercises to come in and eventually work in groups. And so our notebooks might look something like this. If you haven't seen a Jupyter notebook, this is a very stripped down, simplified version to showcase how we can thread together the mathematical representations, the narrative text, the executable code, and of course their visualizations. And so we have this nice integrated environment where they can interact with everything without having to move between different media. We have them work in groups, so this is not a lecture-based course. Students come in, they bring their laptops. Sometimes they're in, on the left, these tech-enabled classrooms where they can plug in and share their screen. In some cases, we just have to push some tables together and have them work with whiteboards there at the space. But the instructor is actually there embedded in the groups, helping them sort of answer questions, ask questions, facilitate the learning. And we have graduate TAs and undergraduate learning assistants who are in this space helping as well. As we created this course, we saw a lot of growth in demand and interest. And so over time, we've seen this rise to, I think we're something at like 350 students per semester at this point in this introductory course. And what I want to highlight, and the reason I put this up here, is much of our early growth was physics and astrophysics students. And part of that is because at MSU, when we proposed this course, physics saw it as an opportunity to integrate computation into their curriculum in a very significant way. And so a lot of our early growth were physics majors, astrophysics majors who were required to be there, but also the faculty wanting them to develop those skills so that they could do more in their third and fourth year coursework. Okay, so what does this look like? How has physics done this at MSU? Physics and astrophysics. And so now astro majors, physics majors would go through the standard sort of physics progression. That's what's happening as you go down the table here. But then in their second year, they're taking this interdisciplinary computing course so that by the time they get to, and there's a lot to digest here, I'm going to skip past it. By the time they get to things like quantum, E&M, stat mechanics, the instructors teaching those courses they already know Python. They know how to make plots. They know how to do visualizations, so they can start integrating into their coursework. And depending on who's teaching the course, it might take a while. And so Quantum 2 was only just recently updated a couple of years ago, and it's continued. The pandemic kind of put some things on hold. But really, the thing that my colleague Danny Caballero has highlighted is that the external support of a program like CMSE and a course like CMSE 201 can accelerate the process of integration. And so he likes to highlight this as like, by having the students go through this very active hands-on learning experience to learn how to do computing in an applied way, they can start integrating it into their coursework. And we even try to integrate problems that are relevant to those physics majors, as I mentioned earlier. And so they might have something like modeling a skydiver, modeling a bungee jumper, and again, turning math into code, and then trying to use it to understand a problem. So I think that's it. What I wanted to highlight here at the end, I'll leave it up here, is we've created a computing education research lab to better understand how students learn in this environment. And that's what I've been doing with my research recently. I'm probably a little over time. Sorry about that. I'll pause for the questions.
Cool. Thanks, Devin. That was great. There are a couple questions. First from Michael, are students required to have laptops at MSU? And what happens if students only have a Chromebook that might not be able to run locally?
Yeah, that's a really good question. So I'll actually drop this out so you can see folks. So MSU does require that every student, as a student at MSU, have a laptop. Now, they pretty loosely define what laptop means. And so Chromebooks do technically pass. And so that can create some problems because you can't install a lot of our software locally. Our solution to this is we actually have a MSU supported resource. We have a Jupyter Hub server. So students just need a web browser to use the full Python interface that we use in class.
Okay, nice. There are some more questions, but we can leave those until
I'll
the
really
end.
quickly answer Alice's. It's about 6 to 8 sections per semester.
Thank you.
So thank you so much, Devin. And let's move on to our second speaker of the day, Stella Offner. Stella is an associate professor of astronomy at UT Austin and was an NSF Astronomy Prize postdoctoral fellow at Harvard Smithsonian Center for Astrophysics and NASA Hubble postdoctoral fellow at Yale prior to this. Stella's research focuses on understanding how stars such as Sun form by combining numerical simulations, observations, and observational modeling. And today, Stella will be talking to us about graduate level computational astrophysics and her experience at UT Austin. So Stella, if you would like to start.
Sure. Let me just start a timer. I don't think I have that many slides, but okay. So thanks very much for the invitation. My research area is in computational astrophysics. So I've been working in this area for a long time and is near and dear to my heart. But that said, I have only recently and a year ago developed and gotten to teach a graduate level computational astrophysics class. I've been able to integrate computational methods into other graduate classes, but this is the first time I had the opportunity to actually develop and teach a class just devoted to this topic. So I'm very interested to hear also what other people are doing to see if I can adapt some of that the next time I teach it. All right, so I want to give an overview of what the class was. I taught it in a very fraught time, which was spring of 2022, and this was as we were, Texas was transitioned back to online, back to in-person learning. But then there was a surge of, COVID. And then, so we started the semester online for a couple weeks, and then we did hybrid for 2 weeks to make the students comfortable. And then I went back to all in person. But the goal of this class was to be primarily lecture-based, but with interactive discussion questions so that we'd break up the lecture and have students have an opportunity to think about things and discuss them. And I'll give an example of that. So there's 6 homeworks, a final project, and a report and presentation. So sort of a mini research project at the end. And I also had guest lectures. I view computational astrophysics from a very star formation-y perspective, but I wanted to also have other people come into the class and tell about their particular areas of astrophysics that they do research in. So here's the beginning of my syllabus. I really wanted to focus on the physics of the astrophysics. So I picked key astrophysics and then broke it down by methods. So in hydrodynamics methods, we focused on grid-based codes. In gravity, we focused on particle-based codes. We did radiation and focused on Monte Carlo and ray tracing methods. Then we had MHD, in which case we did Lagrangian and hybrid methods, because what I did was have them get up to speed with Gizmo, and then run Gizmo for homework, and then run Gizmo for their final project. And then I had some miscellaneous topics. So my course objectives. So I think I wanted two main things. So there was two types of students in the class. There are students who were really focused on computational methods and through their research. So these are pretty, in my opinion, hardcore people who really need to get into the guts of different codes and really understand how they work and be able to even extend them and implement their own methods. And then there was a group of computing curious students, I would say, who thought it sounded fun, but their backgrounds were mainly in observational projects. And so there's really two different sets of objectives. Broadly, I wanted students to be able to understand the landscape of numerical methods in use and their strengths and weaknesses. So whether or not your research is computational astrophysics based, you're going to be reading papers in which numerical methods are going to be used. You need to be able to ask the appropriate questions and assess for yourself whether the results are robust. And so that was really important across the board, right? So be able to evaluate the accuracy of the modeling and be able to put codes in context. Then I wanted students to be able to experience writing their own methods, for example, 1D hydro solver. And I wanted them to also be able to use public astrophysical codes. And it was very important to me that students not treat these codes as black boxes and to really open up the files, look at the routines, look at the documentation, and really try to understand how they were working, even though many of these codes are very complex and it's hard to get a handle on them. Right, so then part of the course was about parallel computing. So I got them accounts on TAC, the Texas Advanced Computing Center, and they got to run their jobs in parallel. And then of course they're running Gizmo. So they got to basically do their final projects using TAC. So that was another skill set. Most students come in, not having used TAC, particularly if they're observational background. And so that was an important learning experience for them. And then last, I know that students, there's no way I can cover everything in detail that I wanted to cover. So I want students to be able to find resources they need to develop methods themselves coming out of this class. And finding a textbook is hard. And so I did use a number of review articles as part of the resources for the class. And so I set up those resources in part, so we're not going to go into this 100-page, review, but we'll look at a couple of sections. And then if you need to go back later and work on developing this, you can go back and you know where to start with that article. And a key point is that this class was not about teaching programming and not about teaching data analysis. And sometimes students, even grad students, are very confused about what the definition of computational astrophysics is. And to me, this is research-based high-performance computing. And so students were allowed to use whatever programming language they wanted. They all chose Python, but basically the focus was on the modeling of physical processes using high-performance computing methods. So this is reading and lecture. So the way I do my lectures is I have slides and I have an iPad, and then I basically write on my iPad. So it's a partial set of notes, and then the benefit of this is that then I can save it, export it, and then share it. And so here's some examples of slides on the left. On the right is my list of resources, including Michael's book on here. But yeah, so it's a really broad range of things I had students looking at. So challenges. The pandemic was really detrimental to this class, and I think it went very differently than it would have done before the pandemic. In terms of collaboration, students got used to working alone, and some of them just did not want to work together. They also transitioned. Many of the students preferred the convenience of being virtual, and they really resisted me going to, back to in-person learning. There was also a clear difference in preparation for the students and the difficulty of classes they were accustomed to. Maybe you guys have experienced this as well, that during the pandemic, the expectations for workload were changed. And so students really struggled that. There's uneven preparation and programming. I think students did all right, particularly being allowed to choose their own coding language, but that was a challenge. Uneven level of interest, uneven level of astrophysics knowledge. So we don't have a course sequence. So that meant that for each of these topics, I had to give lectures on that physics to make sure they were all on the same page. And this is my list of future revisions, but I'm really interested in hearing some other ideas, and I've exceeded my time, so I'll take my one question now.
Great, thank you, Stella. This is great. I want to echo Michael's comment in the chat that this sounds like a really great course. And I do have some questions, but if there is anybody in the audience that has a question, I would be happy to let you ask. And okay, quite. So one question I had is, in your outline, you had a discussion section that was 15% of the grade. And I wondered, so what, I guess, how do you evaluate that?
Yeah, so this is a combination of participation, showing up in class, not necessarily asking questions, but, engaging with the material. So if I ask a discussion question, I can see students talking to one another or working on the problem. I do, during the guest lectures, I told students that part of that participation was paying attention and asking questions there. So that was part of that. So I kept a record of, when the students were there and who was asking questions, and that's what went into it.
Okay, great. Thank you.
Right. Thank you so much, Stella. And our third speaker for today is Ariyeh Mahler. I'm sorry if I am saying your last name wrong. Ariyeh is a professor at CUNY City Tech in New York, and has an impressive teaching portfolio and has taught several courses in physics. Ariyeh did his PhD and master's from University of California, Santa Cruz. And his research interests involve formation and evolution of galaxies, gaseous halos, intrinsic properties of galaxies, and gravitational lensing. Would you like to take it away, Ariyeh?
Certainly. Oh, wait, where does it see? Okay. Thank you. Nice to be here and be talking about this issue. Just to give some background as to my particular experience with having students, which puts me somewhere in between our previous two speakers. At my campus, we offer computational physics as our major instead of a traditional physics program. And so all students are required to take a computational methods course. Our students are primarily underrepresented minorities and first generation in college, English may possibly second language. So our student body is very representative of the kind of people who have less experience and may have less of a background with both with computing and both with feeling comfortable, taking these kind of steps. I think very luckily for us, or by design, our undergraduate computational course is both a lecture and a 4-hour lab, which gives a lot of time to be able to actually work with students and help them go over roadblocks and debug and things like that. I think this is one of the general difficulties in this course, is that most of the time it's primarily a lecture. And so if you take time out to have more kind of people working with students, you're eating out of your lecture time. So you have this much more tighter schedule. So this is the kind of thing people at the level where you're starting to be able to suggest how this course should be implemented. You may want to think about having more time for labs. And I also teach at the graduate level the same course in our graduate physics program. So the first thing I just wanted to mention is teaching computational physics as opposed to computational astrophysics. Has already been brought up. The difficulty of subject material is quite hard to cover things that are would be interesting to all students and that you might have the expertise to actually cover. This is particularly hard if you're doing computational physics, because I assume almost everyone here is in astrophysics. So at least if you're not in every area of astrophysics, you're aware of them, but physics is a vast discipline, and you probably are not keeping up on what's going on in computational molecular physics or in atomic, solid state, a bunch of stuff like that. I recommend Mark Newman's book. There's probably a bunch of other good resources as a place to find a lot of examples of other areas of physics that you may not have expertise in. This is really helpful because if you have students who aren't there for astrophysics, you don't want to just be teaching astrophysics and have them not really learning about the algorithms and methods because they're like another astrophysics on board of that. It's good that we're astrophysics because we tend to be the most popular subdiscipline for people who aren't in it, right? But especially in the graduate level, if you have people who are spending all their time, doing waveguides or solid state or electromagnetic transmission, you'd like to touch upon their disciplines when you're teaching too. So it can be very helpful to be able to have examples, exercises, and homeworks from different areas. It's even possible to have the option of letting students choose, if you're teaching let's just say numerical integration, start off something fairly simple and let students have options of a problem that does that for astrophysics or that does that for stat mech or something, so that they have, can do something nearer and dearer to their hearts. The main thing that I wanted to kind of broach in this talk is what is it that we are trying to do? I think that what I see a lot of times, people teaching computational techniques and coding in general, we have a problem that we have as individuals usually have a lot of experience in this. We have a large body of information, and it's an overwhelming amount of information for our students. And so I think thinking of what we're doing, not so much as trying to tell them everything they could possibly need to know to be able to, run their own simulations, but instead to think about that our main job is to curate that information, to cut it down to the smallest kind of bits that they really need to know or that are really interesting, and it may take them would have taken them years of experience to find that that's the thing that really needs to be known, is the goal that we're trying to do. Okay, so I think that that's a key feature. I'll give an example of what I mean by that in this next slide, which is for Git. Okay, something that probably many of us will want to cover as a topic for them. When I introduce Git for students, I teach it as it's only 5 commands in Git, right? Which is kind of the opposite of what Git is. Taking it down to being almost as least useful as possible, right? So I just teach them, you clone a repo that you set up in GitHub, so you don't have to learn anything about doing that. You just need to know how to add, commit, push, and do a pull. That's it, okay? And just practice those. And then I give homework, and their homeworks, I have them push to a repo for submission and practice those commands over and over again until they know this. And then when you start teaching the next things that they can learn, right, they already have the basis there, right? That's kind of already at muscle memory kind of level. And then you can start adding more information on. And I think in general, this is my kind of point I would say from experience, is that what's really important when teaching and coding and computational techniques to some extent is this kind of building of layering. Students are going to primarily learn what they need to learn at that time, and they're going to basically ignore and be overwhelmed by anything else than what they need to learn. So kind of trying to structure your course of what you need to know, and then what you need to know, then you have that, and what you need to know is, I think, a crucial aspect of being successful in teaching for students. And then finally, as far as goals go, as Stella brought up a lot of these points, you have a bunch of students in these classes. Some of them are going to a place where maybe they're going to develop code on their own and be contributing to large code projects for a community, but not many of them. Okay, many of them may use code a little bit to do something, or use code that's been developed by someone else and need to understand certain aspects of it. All right, but it's not clear that that's the majority or if that's, roughly half. And most students are mostly going to just be either running someone else's code without understanding what's going on, or just seeing the results of code that's been done. And so I think while we want to be able to reach all these students, it's important to remember that the vast majority of them are not going to be developers probably. And so we want them, as Stella mentioned many of these things, so I'm a little bit repeating here, but I think it does bear repeating because I think it's a key point. Now, the most important thing I want them to walk away with is really a suspicion of other people's work when they use code, right? Being able to ask the questions, really, so that this works, and what's the resolution, and what do you need, what time it's taking, what assumptions do you make, and what did you have to reduce the problem by eliminating to make this work, and where are you using an effective model, and what subgrid, right? The kind of questions that are healthy, right, for an environment where people are using computational results, but the community needs to be able to understand those results in the context that they're done, right? And then also, the truth is why it's great to be able to understand every tool you use and to be able to look under that, not have any black boxes and be able to know what you're doing. It is also difficult to do everything, right? And most of us have to take some black boxes at some times, right? So again, you want them to have some understanding that it's not just entirely black box. You want to shade a little gray to understand when you get error messages or it doesn't work, or if you get a result that doesn't seem to make sense, you ask the right questions. But I think we have to accept that they will probably use a lot of fairly black boxes, and that we can't just eliminate that. We want them to be able to ask some of the questions, think about where you would look for more information, be able to do sanity checks to make sure things are working out, to think about understanding what computational methods do, right? And so they also where they may be fall short, where they may give you results that aren't realistic. And I can stop it there and take any questions.
Great, thank you. That was very informative. And I also agree with Michael that having a whole computational physics major is I haven't heard of that before, but that sounds really nice.
Yeah, it's we are a little bit as the technical college of the system, we're forced to not be repeating things exactly. So there's some aspects of that, but I do think that if you're thinking about not just going to graduate school, right, as far as skills go, I think it is useful to think of it as a larger family of skills, of problem solving and thinking about the world, that kind of thing.
Makes sense. So we wanted to leave 20 minutes for discussion, and so for the interest of time, maybe we can just move on to Michael's talk, and then we can just address all the questions at the end, if that's okay with you.
Are we going to introduce Michael quickly?
I'll try to be. Oh, I'm sorry. I'm sorry, Amber.
Hi, Michael. So Michael is
Hello.
a person, if you've been attending these sessions, who doesn't need a lot of introduction, but we are going to do a brief blurb on him anyway. So Michael is a leading computational astrophysicist and focuses on developing codes and algorithms for X-ray binaries and supernovae and novae, and has developed many different codes that are widely used by the community, such as Maestro, Pyro, Castro, Pinuke, Astro. And not only this, also has these famous Jupyter notebooks and codes that are available in the domain of educational codes, such as Intro to Astronomy animations, numerical methods, and the Jupyter notebooks. Did I mention those? I love those. So yeah, so Michael will tell us about some of his experiences in teaching computational astrophysics.
Thanks, Amrita. I'm going to echo a lot of what was said already. I've taught roughly 4 different classes on computation here at Stony Brook. At the undergrad, just this last semester, I taught an intro to computational astro. It was all Jupyter based. I'll show some resources from that at the end. It was the first time I taught it. It was a special topics course. It was the first time it was taught here. And so I have a lot of ideas on how to improve it. At the grad level, I've taught Python for scientific computing. I started that class here 10 years ago. It's a 1-credit seminar, all based on participation. And I have grads from 12 or 13 different departments, even some other faculty sitting in, taking the class. And so that's proven to be popular. And I've taught both of our 2-credit, our 2-course sequence for computation at the grad level. As Ariyeh said, this is physics and astro, so I had to relearn how the Schrodinger equation works, and there's also some challenges there. So I think the first challenge, though, is as Stella mentioned, what is computational astrophysics? And I think we all have our own definition for that. And sort of in line with what other people have said, I think we really have the need for 3 different classes when we talk about teaching our students. And one is an introduction to programming. And even at the grad level, not all of our grads come in knowing how to program. When I teach this, I teach Bash and Git and a language. And in the grad level, I teach C++, because that's the main language I use, and the department seems happy with that. I think we need a data science course, and I shouldn't teach that at all, because I've never touched a FITS file, for instance. And sort of more in my comfort zone is simulation, high performance computing, and that sort of aspect. And that's what Stella had talked about. And I think they're all three different courses, 3 different skills, and probably our grads and our majors should be exposed to all of them. And the language likely differs between them. Python dominates in data science. In HPC, it's C++ and Fortran. As I said, C++ is the main language I use, but I've been using Python for decades, and that's what I teach at the intro level. But I also think students should be comfortable in more than one language. And I forget who said it, but I do the same thing where they can hand their homework in whatever language they want. Some students try to challenge me by picking rather exotic languages, but it all works out. The things that I focus on, and this echoes what others have said, is how we go from an idea that we have, and Devin had a very nice slide of this, to writing the code. And that's the main thing we want students to understand, is how to work out in your head what an algorithm looks like. As Ariyeh said, I like to teach computational skepticism. You should be, you should look at what people report and ask, did they really understand the methods that they use and the limitations of the methods? And this goes on to how to test methods. I love to have students run convergence tests to see if they get the order of accuracy that the algorithm is supposed to get. And also when to write your own stuff and when to use the library. I think this was also said, this is the problem with going last. I like to implement the core methods from scratch before we use some other black boxes. When I teach machine learning, I write a neural network from scratch for class, and we do the character recognition and all that stuff before we go on and do, use something like Keras or TensorFlow. And the reason I like to emphasize this is that even if as a student, you're never going to use your own solver, because you're going to use codes that have been written over decades by large development teams, you learn a lot by putting it together, and you'll understand other people's code and the design decisions they made if you had to go through that process on your own. I also think software engineering should be integrated throughout. At the grad level, I use GitHub Classroom to turn in your homework. It's a really nice GitHub feature. You set up a classroom, every student gets a repo that's private, shared just between you and that student, and they click on a link to get the homework, and it populates this repo with a template or whatever you want. And then to turn in their homework, they have to know how to use Git. So of course I teach Git, but it reinforces the idea that they should be using version control. And then I like to make everything open. And I think we should all strive to do that. There's so much good content out there. None of us are experts on everything, certainly me when it comes to data science. And I like to, make my resources available. And ideally, in the limit of infinite time, I'd love for us as a community to sort of put together some unified resource that we could all use to make mashups for our classes when we teach them. So this past semester, I really dug into JupyterBook, which is a really cool way of creating web pages from Jupyter notebooks. It's a project as part of the executable books project. There's a lot of libraries that go into this. And I'm going to show you how that works. You write a table of contents in YAML, which is one of the many markup languages. You use Markdown or Jupyter notebooks, and they can be combined into and converted to web pages. You can automate it with a GitHub action. So I just push to my repo and it automatically builds the book, the web page, and it's updated in a few minutes. And so I have an example, which if I can, let's see if I can load, is this is the course I taught last semester on computational astrophysics. So this is the GitHub repo. This is the just the, what is this? This is the short GitHub action that if you never wrote a GitHub action, no one ever writes one on their own. We just copy what someone else did. It downloads Python. It uses JupyterBook to build the book, and then it pushes it to the website. And this is the table of contents that you write. And it's, you know, this is YAML, but it's just, you know, it's like you would write a table of contents on your own in ASCII. You give chapters and what file provides the chapters and so forth, and it writes this book. And so this is the web page for what I taught last time. And what's really cool is that it has some functionality which helps you. And so the reason I asked Devin about what if someone can't run on their own computer, you could do, let's see, so let me find a notebook that actually has something interesting. So here's a notebook on ODE integration. They can, if you go to the little rocket ship, you can run it in the cloud directly. And so I can launch it in Google Colab. They don't have to install anything locally. They can do this all from the web. It'll automatically launch in Google Colab. This is the peril of doing a live demo. Here we go. And then Google will just say, hey, Google didn't write this notebook. Are you sure you want to run it? And you just trust me. And then you can go ahead and you can run the notebook and you can play around with orbits and things like that automatically. And if you want, they can go to GitHub directly and they can open issues. You can download the notebook as IPython notebook or as a PDF. You can go to dark mode if you want, which is fun. People like dark mode. And so I put this together last semester when I wrote this computational astrophysics class. I bit off a little bit more than I could chew, I think, and I ran out of steam by the end. But this is sort of, after teaching these computational courses for a decade or so, this is the best way that I've come up with to present the material. It's relatively easy for me. I just write Jupyter notebooks. I just push them to Git and the web page is built. And it allows the students to read ahead outside of class, to replay everything I do in class. And it also is more accessible for students who don't have fast computers and things like that. The main thing I would do different, of course, if I get a chance to teach this class again, oops, I can't tab and talk at the same time, is try to flip it some more. So I tried a little bit, but you know, it was the first time I was teaching it, but I'd like to have more working through notebooks outside of class and doing stuff interactively. And I'll just end with, as I said, I put all my course material up online. Most of it's on GitHub. Some of it, if I haven't taught it in a while, isn't. But I posted these links as well in the chat for our meeting. And thank you for our 3 other speakers. Teaching computational astro is something I really enjoy. And so it's really great to hear from all of you about your experiences.
Great. Thanks, Michael. That was great. Before we move to questions, I think that Amruta had some things that she wanted to say. So I'll turn the floor over to you.
Yeah, I just wanted to take a minute for 2 things. One, I wanted to introduce Sam. So Sam is at the Vanderbilt University and would be joining the VAST team going forward. So let's welcome Sam to the team. And we will see Sam hosting emceeing in the coming year. And talking about the coming year, we just wanted to thank you from all of our team for being with us through this first initial year of starting VAST out as an idea that brilliant idea that Michael had. And it has been successful beyond what we had initially thought, and which is why we will take a short break in August, but starting September, we're going to start season 2 of FAST, basically. And there are new exciting plot lines or characters that would be introduced in season 2, including a trial chapter that we would be running. So stay tuned, and we would be very excited to have you all with us, including Sam, starting September. Thank you, and we can move on to the Q&A.
I have a question for all of our speakers, if I can ask it.
Yeah, of course.
So is there any inclusion of the concept of open source and what that means, and licensing software and making it available for others to look at and perhaps use? So I'm very big on, if you're writing computational methods for research, those methods should be open so others can look at what you've done. No black boxes in science kind of thing. So so is that included in your courses? Could it be, if it's not already? Please. So that's a question for the speakers. I mean, do you approach this at all, and if so, how? So Michael says,
I'll start with that.
Okay.
Like in the general, going to the level of licensing and the complicated things, that's I think a little past where we're usually going for students are at. In the first level of the first important thing, I think for many students who have mostly used computers and only bought things from Apple or Microsoft, is the level that you will be using code that's not developed only by companies. And that means it doesn't have the same, way of always working or taking care of your needs. You have to kind of meet to it more halfway. So I think that the main thing that most aspects I bring in open source is one that, we're going to install packages that are developed by communities, people who are voluntarily doing it and sharing it. This is open source. And so therefore, the updates and versions and stuff, you may have to do some work on your end. You can't just expect everything to work perfectly for you. And two, I say, this is a big part of why computation advances. This is, why Python is a language, besides the fact that it's so popular because of its, syntax, is because people make a lot of packages in it and they share it with other people. And then I point out that this kind of working and sharing, in the classroom, collaborating with each other, to kind of model this behavior, you want to think open source of like sharing with each other. There's nothing wrong with sharing your code. Just don't copy other people's code, but work together with it. So I bring it into this kind of the community of coding thinks about sharing things and not having to reinvent everything all the time. But then I don't think that, I think those next steps of kind of going to farther along. I think you're starting the process of it at this point.
Well, it seems that if you're using something like GitHub, it would be very natural to say, choose a license. This one is popular. So I never tell people which license to choose. I will say in astrophysics, this one, the MIT license, is particularly popular, but then because GitHub asks you to assign a license. So it seems to me that would be a good way of starting to build those good habits for open source. So thank you for that answer. And I saw Michael posted something in the chat too. So thanks. Thanks, Michael, for that.
Yeah, that book, it's a little old now, but the Effective Computing in Physics has discussions on licensing and all sorts of things.
Yeah. And we have resources on the ASCL news part that it relates to licensing that actually points people to other sources. So I may need to add that one. Thank you.
That would be great. I just posted a paper to archive recently, and I never remember which license to choose because it's all very opaque. And so having a better understanding of the details of those would be something I would have liked to have starting out. Awesome. Okay, so we have about 10 minutes left. If anyone has a question, either put it in the chat or you can raise your hand like everyone just did. If you raise your hand in Zoom, then I can see and I will call on you. And so yeah, Amruta, go for it.
I have a quick question about when it comes to testing codes, what kind of standard practices or references do all of you follow?
So I guess I cover some of the testing codes. And part of what we do in class in the readings is we will look at some method papers. And as you know, method papers typically include code tests and comparison tests. So the Gizmo 2015 release paper is a really good example. So I have them look at that. And then as part of the homework, I also have them run some of the problems with different resolutions and then compare the accuracy of the solution. So yeah, I think I use the method papers as a context for discussing how we test and compare the results of codes.
I guess I'll jump in and just add, I don't think I have any specific references that we normally use sort of students, but we do try to instill the concept of like testing, right? You're going to write an algorithm that you think does this particular thing. How do you know it does that? So we try to get students to get at the idea that once you write something, you should try to think about like, what are all the edge cases? And have I actually confirmed that that's true? And does it have bizarre behavior at certain points? We're not dealing with sophisticated algorithms in a 200 level course. We do want to get them used to the idea that you shouldn't just run a code and assume that the answer that comes out is exactly right? The idea that you should, I think maybe Mike mentioned it, but code skepticism, like, does this actually do what I want it to do or not? And does it match my intuitions? I talk a lot about like run a test where you think you know the answer and see if your code aligns with that. So we do talk about the importance of testing, but I don't know that we've formalized it maybe in the ways that you're asking.
Great, thank you. That's good.
Sam, there was a question in the chat by Carla. Up a little bit if you scroll.
Oh yeah,
Yeah,
okay. Yeah,
thank
go ahead.
you.
You can ask it aloud.
Yeah, thank you for the session. I have found a strong resistance to the students to change methods, functions, even change from Jupyter notebooks to scripts. And I think that the root is that they fear that suddenly if they change the command line or whatever, the script is not going to work properly. So I don't know how you have deal with that, or have you found that? Any comment in that regard?
I'll try to answer or give some answer to that. I completely agree. You get a lot of resistance to trying new things. If it works, don't rock the boat. And my short answer to that is I try to force them, against their will. So you have the advantage of being the instructor. You can make them do things. So in particular, people talked about Jupyter Notebook a lot, and Jupyter Notebook is a great way to get going with coding and to show a lot of things. But one problem is I find a lot of students have no experience outside of the notebook and don't know how to run any code outside the notebook. So I force them to also run, I force them to write a code and run it outside of the notebook as an exercise. And I do that in a kind of saying, you may not like it as much, but it's good to have experience it. So you have to do this for this assignment or for this number of the assignments, and force them out of their comfort zones. And it's also a good technique for when you have very different levels of students in classes, which is often the case. So one thing I do sometimes is, students who are more advanced, I have them move to, using a different method for their how they execute their code, and why students who are more new and are still working on just getting some syntax, let them maintain only working in notebook. So you can kind of force these changes on certain students to push them out of their zones. But yeah, I don't know there's an easy answer besides making them do it.
Thanks. That's a great answer. There's time for maybe one more question, which was
You're a bit low, the volume.
oh, sorry, I put it in my headphones and they don't work so well sometimes. one last question from Holem Cheng, and it's any comment on the research performance of grad students who did or didn't attend any computational class?
I mentioned a little bit on here. Maybe one way to frame it is we get a bit of pushback in our department that at the grad level, we can't really require computation because then they say, what are we going to drop, right? We're already worried that too many students that we have too many classes. We're a big department. We have 75 faculty or so. And so I tend not to see the students who don't do computation. So I don't really know. But I will tell you increasingly, there is interest in the students to do computation because increasingly they want to do their degree and then go into the high-tech world after grad school. And so I think that computation classes are growing in popularity. I don't know about how the impact of the research is for the students who don't take it though.
Sure. Stella, Ariyeh, or Devin, do you have any comments on that?
Yeah, I think it's only anecdotal though. The students, I had a few students who took my class take the codes that I use in the class and then go and use them for research. So I think that's a success where I've managed to demystify the codes and they seem friendly enough that they actually want to keep using them. But outside of that, it's very difficult to assess because, you know, this isn't small number statistics and, you know, it's yeah, what is the metric you would use to determine success? Like, are the students, you know, scared out of computational research? Do they keep using it? Like, I don't know what metric I would use to evaluate the success here.
Okay, that's great. There were some more questions, but unfortunately we've reached the time. And so I want to, in the last minute or so, turn this back over to Amruta, or MC, to close this out.
Sam, you were still a little bit low. I'm sorry.
Sorry. Get some new headphones. I was just saying that we're near the top of the hour, and so I want to. There are more questions, but unfortunately we've reached the end of the time, so I'm turning it back over to Amruta to close this out. You're muted, Amruta. Sorry.
Yeah, thank you. Thank you to everyone for being with us today. And for all the questions which we couldn't answer, please leave them either via the email for the VAST and or discuss them in the VAST Google group that we have initiated. And thank you for being with us through this year. I hope all of you have a great time off and some time off for summer in August. And see you all here in the same virtual space starting September.
Applause for all our speakers. Yay.
Yeah.
Thank you.
Thanks, everyone.
Thank you.
So, bye.
Thanks so much.
Thanks, everyone, and Sam.
Yeah. Thanks, Sam. You did great.
Thanks. I think you all.